Shortest paths and distance vector protocols. One important application of the shortest path problem is for routers in a communication network to determine the most efficient path to a destination. We represent the network using a graph in which the nodes correspond to routers, and there is an edge between V and W if the two routers are connected by a direct communication link. We define a cost CVW representing the delay on the link VW. The shortest path problem with these costs is to determine the path with minimal delay from a source node S to a destination T. Delays are naturally non-negative. So one could use a Dijkstra's algorithm to compute the shortest path. However, Dijkstra's shortest path computation requires global knowledge of the network. It needs to maintain a set S of nodes for which shortest paths have been determined and make a global decision about which node to add next to S. While routers can be made to run a protocol in the background that gathers enough global information to implement such an algorithm, it is often cleaner and more flexible to use algorithms that require only local knowledge of neighboring nodes. If we think about it, the Bellman-Ford algorithm discussed in the previous section has just such a local property. Suppose we let each node V maintain its value M of V. Then to update this value, V needs only obtain the value M of W from each neighbor W and compute minima of CVW plus M of W, where the minima is taken among all possible W in V based on the information obtained. We now discussed improvement to the Bellman-Ford algorithm that makes it better suited for routers and, at the same time, a faster algorithm in practice. Our current implementation of the Bellman-Ford algorithm can be thought of as a pool-based algorithm. In each iteration I, each node V has to contact each neighbor W and pull the new value M of W from it. If node W has not changed its value, then there is no need for V to get the value again. However, V has no way of knowing this fact, and so it must execute the pull anyway. This wastefulness suggests a symmetric push-based implementation, where values are only transmitted when they change. Specifically, each node W whose distance value M of W changes in an iteration informs all its neighbors of the new value in the next iteration. This allows them to update their values accordingly. If n of W has not changed, then the neighbors of W already have the current value, and there is no need to push it to them again. This leads to savings in the running time, as not all values need to be pushed in each iteration. We also may terminate the algorithm early if no value changes during an iteration. Here is a concrete description of the push-based implementation. Push-based shortest path of input parameters G, the graph G, S, and T. Let n equals to the number of nodes in G. We have an array M of V, where V is the vectors, the vertices. Initialize M of T equals to 0, and M of little v equals to infinity for all other little v, which is in vertices capital V. For I equals to 1, 2, 3 until n minus 1, there is an inner loop. For W in V in any order, if M of W has been updated in the previous iteration, then for all ages VW in any order, we let M of V equals to the minima taken among M of V and CVW plus M of W. If this changes the value of M of V, then we let first of V equals to W. And 4. If we break out these two levels of for loop and go to the first level of for loop, we finish the for loop by if no value changed in this iteration, then end this algorithm. Okay, after we finished all the iterations, we return M of S. In this algorithm, nodes are sent updates of their neighbor's distance values in routes, and each node sends out an update in each iteration in which it has changed. However, if the nodes correspond to routers in the network, then we do not expect everything to run in lockstep like this. Some routers may report updates, much more quickly than others, and a router with an update to report may sometimes experience a delay before contacting its neighbors. Thus, the routers will end up executing an asynchronous version of the algorithm. Each time a node W experiences an update to its M of W value, it becomes active and eventually notifies its neighbors of the new value. If we were to watch the behavior of all routers interleaved, it would look as follows. Asynchronous shortest path of input parameter G as entity, n equals to the number of nodes in G, array M of V, where V is the vertices, initialize M of t equals to 0 and M of v equals to infinity for all other little v in capital V, declare t to be active and all other nodes inactive. Now there's a while loop. While there exists an active node, we choose an active node W. Then there's an inner for loop for all edges VW in any order. Let M of V equals to the minima chosen between M of V, the original M of V, and CVW plus M of W. So if this changes the value of M of V, then let first of V equals to W. Let V becomes active. If we break out of the for loop, then we let W becomes inactive because we have finished the update of the active node W. Now one can show that even this version of the algorithm with essentially no coordination in the ordering of updates will converge to the correct values of the shortest path distances to t, assuming only that each time a node becomes active, it eventually contacts its neighbors. The algorithm we have developed here uses a single destination t, and all nodes little v and capital V compute their shortest path to t. More generally, we are presumably interested in finding distances and shortest paths between all pairs of nodes in a graph. To obtain such distances, we effectively use n-separate computations, one for each destination. Such an algorithm is referred to as a distance vector protocol, since each node maintains a vector of distances to every other node in the network. Problems with the distance vector protocol. One of the major problems with the distributed implementation of Bellman-Ford on routers, the protocol we have been discussing above, is that it's derived from an initial dynamic programming algorithm that assumes h costs will remain constant during the execution of the algorithm. Thus far, we've been designing algorithms with the tacit understanding that a program executing the algorithm will be running on a single computer or a centrally managed set of computers processing some specified input. In this context, it's a rather benign assumption to require that the input not change while the program is actually running. Once we start thinking about routers in a network, however, this assumption becomes troublesome. H costs may change for all sorts of reasons. Links can become congested and experience slowdowns, or a link VW may even fail, in which case the cost CVW effectively increases to infinity. Here's an indication of what can go wrong with our shortest path algorithm when this happens. If an HVW is deleted, say the link goes down, it is natural for node V to react as follows. It should check whether its shortest path to some node T used the HVW, and if so, it should increase the distance. Using other neighbors, notice that this increase in distance from V can now trigger increases at V's neighbors if they were relying on a path through V, and these changes can cascade through the network. Consider the extremely simple example in figure 6.24, in which the original graph has three edges SV, Vs, and Vt, each of cost 1. Now suppose the HVT in figure 6.24 is deleted. How does node V react? Unfortunately, it does not have a global map of the network. It only knows the shortest path distances of each of its neighbors to T. Thus, it does not know that the deletion of Vt has eliminated all paths from S to T. Instead, it sees that m of s equals to 2, and so it updates m of v equals to cvs plus m of s equals to 3, assuming that it will use its cost 1h to s, followed by the supposed cost 2 path from s to t. Seeing this change, node s will update m of s equals to csv plus m of v equals to 4 based on its cost 1h to v followed by the supposed cost 3 path from v to t. Nodes s and v will continue updating their distance to t until one of them finds an alternate route. In the case as here that the network is truly disconnected, these updates will continue indefinitely, a behavior known as the problem of counting to infinity. To avoid this problem and the related difficulties arising from the limited amount of information available to nodes in the Bellman-Ford algorithm, the designers of network routing schemes have tended to move from distance vector protocols to more expressive path vector protocols, in which each node stores not just the distance and the first hop of their path to a destination, but some representation of the entire path. Given knowledge of the paths, nodes can avoid updating their paths to use edges they know to be deleted. At the same time, they require significantly more storage to keep track of the full paths. In the history of the Internet, there has been a shift from distance vector protocols to path vector protocols. Currently, the path vector approach is used in the Border Gateway Protocol (BGP) in the Internet Core.